So what we are going to be talking about today are positive feedback op-amp circuits. Get myself organized here. That is not how you spell feed. So by definition, a positive feedback op-amp circuit is any op-amp circuit in which positive feedback is employed. I know that's not wildly relevating or anything like that. So let's talk about exactly what I mean by positive feedback. If I have an op-amp, this is my non-inverting terminal, here's my inverting terminal, here is my output terminal. I have VCC plus, VCC minus, like so. So if my circuit contains a feedback resistor that connects the output of the op-amp to the non-inverting terminal, this is positive feedback. Okay. This guy could be connected to ground or a reference voltage or a resistor network or whatever. Similarly, we may additionally have a resistor network and then potentially an input voltage. It doesn't matter if we put our input voltage on the positive, the non-inverting terminal or the inverting terminal. What makes it a positive feedback op-amp circuit is this feedback resistor between the output and the non-inverting input. Okay. So what a positive feedback circuit does is it takes a small amount of the output signal and adds it to the input signal. So that may not make a whole heck of a lot of sense, but you've probably all experienced a positive feedback system in your life. How many of you have ever been to a presentation, assembly, or anything like that and had the speaker's feedback? So what that is when you speak, you create a pressure wave. That's literally what vocal speech or anything that comes out of your mouth is a pressure wave. That pressure wave gets converted into an electrical signal by a microphone. That microphone then goes through an amplifier system and outputs an amplified version of the input signal, your voice, through the speakers. The speakers work by vibrating, creating another pressure wave. Well, if the pressure wave created by the speakers gets picked up by the microphone as well, it cascades over and over again until all you're left over with is that high-pitched squealing noise. That is a positive feedback scenario. So in an amplifier, in an electrical amplifier that has positive feedback, that means that we are still going to be limiting our output signal to either VCC plus when it saturates that way, or VCC minus when it feeds back in the opposite direction. So it's still always going to ramp quickly up to VCC plus as the output or VCC minus as the output. So we don't have a stable system still. All right, so the first circuit that we are going to be dealing with that employs positive feedback is what's called a non-inverting Schmitt trigger. SCHMITT. And it is nothing more than a glorified comparator. So it's a comparator with slightly better functionality, okay? So the circuit is going to look pretty much exactly like the one I've drawn up top here. I'm not probably not going to draw the power supplies anymore. We're just going to assume that they're biased in such a way, or the op amps are biased in such a way that they're on. So we're going to have a resistor R2 in the feedback position. Here's our output voltage. We're going to have a resistor R1. This is where we apply our input voltage. And then on our inverting input terminal, we also apply a voltage. And this is our reference voltage. Okay. Now this guy behaves extraordinarily similarly to a comparator, but the issue here, we're going to see that it's not when Vin is greater than V reference that this thing changes outputs. It's when the voltage at this node connected to the non-inverting input, whenever it's larger than V ref, we should see the output go high, and whenever it's lower than V ref, we should see the output goes low. But there's a disconnect between the input voltage and the triggering voltage that causes the state to swing from high to low. And that's what we're going to investigate. So in using the practical op-amp model, so let's see. Where this is my non-inverting input terminal, this is my inverting input terminal. So this is my differential voltage VD. Here's my input voltage, or input resistance RN. Here I have AVOL times VD. My resistance R out. So this is my bare bones practical model. I'm looking at the output voltage over an open circuit. Oh, let me define this to be R out real quick. So that means that the potential difference between here and here is V out. I have a feedback resistor placed between the non-inverting input terminal and the output terminal. So that means I have this feedback loop up here where R2 is. Between the non-inverting input terminal and some point out in space, I have my resistor R1. Between the other leg of R1 and ground, I have my input voltage. So let's just call this Vn as a function of time. And between my inverting input terminal and ground, I have that voltage V reference. Okay. So before we move along here, does anybody have any questions, comments, concerns about how I've redrawn my circuit using the practical op-amp model? Anybody see anything sketchy? All right. So we're going to be making a couple of assumptions here. Rn is much, much greater than R1 and R2, and R out is much, much smaller than R1 and R2. So if I apply Kirchhoff's current law at my non-inverting input terminal. I get my voltage V plus minus my input voltage divided by the resistor R1 plus V plus minus V minus, which is V ref, divided by my resistor Rin plus V plus minus V out divided by resistor R2 is equal to 0. Fairly straightforward application of Kirchhoff's current law. Now, if Rn is on the order of mega ohms, and R1 and R2 are on the order of kilo ohms, what can we say about the current flowing through Rn? Very, very small, right? So what I'm going to do, based on the assumptions that we're making, is say that the size of that current is going to be negligible in comparison to the size of the current effectively being supplied by the input voltage source and the current flowing through the feedback resistor. Okay, so I'm able to make that assumption under the constraint that Rn is much, much greater than R1 and R2. So what this gives me is V plus minus Vn divided by R1, not Ri, plus V plus minus V out divided by R2 is equal to 0. And I can do a little bit of algebra, and I find that V plus is equal to R2 times R1 plus R2 multiplied by my input voltage plus R1 divided by R1 plus R2 multiplied by my output voltage. Now let's make one other observation here really quick. If the current flowing through this resistor Rn is negligible, then what does that mean about the voltage drop Vd? If we say that this current is for all intents and purposes 0 as compared to this current and this current flowing up, if the current is 0, there should be no voltage drop over our input resistance, which means V plus and V minus represent the same quantity. So V plus is effectively or really, really close to our reference voltage. So I'm going to alter this guy slightly and put V ref here. And this is our governing equation. Our reference voltage is R2 over R1 plus R2 times Vn plus R1 over R1 plus R2 multiplied by V out. Now this is not a traditional input-output relationship equation because the input and the output are on one single side of the equation. So what we're going to do is we are going to solve for the trigger levels here, okay? Because this is a positive feedback circuit, we know that our output is going to be VCC plus or VCC minus. So I'm going to define the upper trigger limit real quick, okay? And I guess I have to do it on this next page. Upper trigger limit. So the upper trigger limit is the input voltage which causes the output voltage to swing from VCC minus to VCC plus. I want to be real clear about that, okay? So the upper trigger limit is the voltage where the output goes from low to high, all right? The lower trigger limit is the input voltage which causes the output voltage to swing from VCC plus to VCC minus, or it's the input voltage that causes the output to swing from high to low. So these are important terminologies because we're going to be trying to find them, and it might seem awkward as to why I'm putting specific values in certain places, okay? So sorry. All right, so we have our equation. V reference is equal to R2 divided by R1 plus R2 times Vn plus R1 over R1 plus R2 times V out. This is just the exact same equation we had a minute ago, but I'm on a new page and we're going to be looking at it a lot, so I decided to rewrite it down. Okay, so if we want to find the upper trigger limit, we know that we're going to have V reference is equal to R2 divided by R1 plus R2 plus R1 over R1 plus R2 times our output voltage, right? Well, our output voltage in this case is VCC minus, because we're trying to find the voltage that causes it to go from VCC minus to VCC plus. So we can rearrange this guy. Oh, sorry, there should be a Vn right here. So we would have Vref minus R1 over R1 plus R2 VCC minus is equal to R2 times R1 plus R2 Vn. So if we solve for Vn, this is going to give us R1 plus R2 divided by R2 times V reference minus R1 over R2 VCC minus. So this is the voltage that's going to cause the output to swing from low to high. Everybody follow my algebra there, right? I made the substitution that because I'm trying to find the upper trigger limit, I know that my output should be low and is going to high. and then simply did algebraic rearranging. So I moved this term to the other hand side and then multiplied by a factor of R1 plus R2 divided by R2. Because dividing by the fraction, dividing both sides by this fraction is the same as multiplying by the reciprocal. Because math, right? For my lower trigger limit, I have the exact same initial equation. Vref is R2 over R1 plus R2 plus R1 plus R2. Now I'm going to have VCC plus. So if I do the math here, I move this to the other side. Vref minus R1 over R1 plus R2. Dang it, I keep forgetting to put that V in there. Sorry. Here is VCC plus is equal to R2, R1 plus R2 V in. And so we get V in is R1 plus R2 over R2 Vref minus R1 over R2 VCC plus. Right. So looks like effectively the same thing, but we need to recall VCC minus is typically a negative quantity. It's definitely smaller than VCC plus. So this quantity is going to be some number minus a negative, meaning we're going to get a high voltage. And over here, we're going to have some number minus a positive voltage is going to give us potentially a negative voltage, at least a smaller one. So we will not, our output will not switch to VCC plus until we exceed this guy. And our output will not switch to VCC minus until we get lower than this guy. So let's throw this circuit into LT Spice and explore this behavior. Says my screen sharing is paused, which means I'm sharing my screen in the wrong way. Share screen. All right. Turn this guy on. So let's see. Universal op amp, as per usual. Let's throw some voltages over here. So what do we want VCC plus to be? Pick a number that's positive. 10 volts, all right. What do we want VCC minus to be? Needs to be a number less than 10. Pardon? Negative 10. All right, that makes it easy enough. VCC plus. That does not look like a plus sign. Goes here and here. VCC minus goes here and here. All right. Just for the sake of argument, because we're just kind of seeing what's going on here, I am going to choose my reference voltage to be 0 volts, so somewhere in the middle. And my reference voltage is applied at the negative polarity terminal, right? Yeah. So let me run a wire from here to here. All right, and now I'm going to have to set up my resistor network. Holy stromboli. I'm going to call this guy B out. Take a resistor, drop it there, drop another one over here. This is where my input voltage is going to be applied. So I should probably define that real quick. Voltage. Ground the bottom. I am going to make this a simple triangular wave. So I'm going to do this as a pulse. So I'm going to say that its initial voltage is minus 10 volts. Then when it turns on, it's positive 10 volts. There is no delay. I'm going to say that it takes 1/2 of a second to rise, 1/2 of a second to fall, and then it doesn't stay on. So effectively, it's rising from negative 10 to positive 10, and then immediately going from positive 10 down to negative 10. And the period will be exactly 1 second, which will make this really easy to look at. That's the wrong thing. The in goes here and here. And I should be good to go. Oh, I need to define resistor values. So just for the sake of argument, let's do 5K on both. All right, so before we simulate this, let's see whether or not we're correct. Okay, so with our numbers, we should see that the upper trigger limit is going to be R1 plus R2 divided by R2 times VREF, but VREF in this case is 0, so that first term just goes away. So that's easy enough. So we're going to have negative R1 over R2 times VCC. So our upper trigger limit is actually going to be 10 volts, so that's not going to work for us. So I'm going to change R2. Hold on. Now I need to check here. R2 is the one in the feedback. So let's make this guy 1K. We're making them different so that we actually have a trigger limit that we can observe. So we do this in a different color. So we should get UTL is negative I should have done it the other way around. Sorry. This is what's confusing me, is that R2 here is R1 and the other thing. So I'm going to be lazy and rename them, so I stop confusing myself. All right, so we're going to make this guy 1 and this guy 5, and now we should get something. All right. Crap. So that's negative 1/5 times negative 10 should be positive 2 volts, right? And then down here, we're going to have the same thing. Lower trigger limit is going to be negative 1/5 times positive 10 is negative 2 volts. So if I've done the math correctly, this is how it should work. Let's run a simulation. It's transient analysis over 5 cycles. And I'm going to plot my input voltage. So we see that it's a simple triangular wave. My output voltage. So every time Vin is 2 or greater, it goes high, and it doesn't, the output doesn't go low until Vn hits -2 or lower. So it's exactly what we expect this thing to do. Now, what I'm going to do is I'm going to change what I'm plotting against. So instead of plotting as a function of time, I'm going to plot as a function of the input voltage. And we're going to see something funny looking if it works right. And I need to delete the input voltage from this signal. And I'm going to change the limits on this slightly. So instead of looking at it from 10 to -10, let's look at it from 12 to -12 so that the axes aren't getting in the way. All right, so we have this funny rectangular shape. This is what's called a hysteresis loop. Anytime you have an input-output relationship that involves hysteresis, that means the system effectively has memory. So this is telling us exactly where the upper and lower trigger limits are because we can see the output switch. So whenever we get higher than 2 volts, it switches to high and continues going. And when we back down, it doesn't go low until we exceed -2. So as it cycles, it goes like this, over and over and over again. You'll deal with hysteresis an awful lot when you get into magnetic circuits because they all kind of inherently have memory. Okay, so, oh gosh, it's been 40 minutes. All right, I was going to do a simple design example, but I don't know that we have time for that. Sure.
Back way back when you were still writing out the phone, you defined you put R reference or voltage reference back into the equation. You took out V and just replaced it with voltage reference. Why would you do that?
So I didn't take V in out. I took V plus out. So here was V plus, V in was always there and it needs to be there.
Right.
I changed this from V plus to V reference. And I did that because we are making an assumption again that if Rn is much greater than R1 and or R2, the current flowing through this input resistance is extraordinarily small. If the current flowing through this resistor is small, the voltage drop over it is very small. And so this terminal and this terminal are roughly the same thing. Yeah, and our simulation verifies that my assumptions are correct. The op-amp model that I'm using has a input resistance of a mega ohm or 2, and we're using kilo ohm scale things here. All right, so do I have enough space? Yeah, I think I have enough space here. All right, the next circuit that we're going to deal with is the inverting Schmitt trigger. This one's going to be much more brief. It is a nearly identical circuit. Here's our resistor R2 in the feedback position. Here's our voltage V out. Here's our resistor R1. Here we apply V reference. Here we apply V. Excuse me. So we could go through the trouble of redrawing the practical op-amp model version of this guy and all that kind of jazz. Or we could do this the significantly easier way. So I'm gonna ask you guys what I hope is a very simple question. What's the difference between this circuit, the inverting Schmitt trigger, and the non-inverting Schmitt trigger circuit we looked at a couple of minutes ago? So I'm not 100%, I think you're right, but I'm not 100% sure that I'm following. So at a more basic level, what on the picture has changed? Let's start there. Vref is where Vin was, and Vin is where Vref was. So that means that our governing equation, we can literally just replace Vin and Vreference and call it a day. So the inverting Schmitt trigger is governed by the equation Vin is equal to R2 over R1 plus R2 times Vreference plus R1 over R1 plus R2 times V out. And now it's really trivial to determine the upper trigger limit and the lower trigger limit, right? For the upper trigger limit, we put V out as the VCC plus. For the lower trigger limit, or excuse me, for the upper trigger limit, we put V out as VCC minus. For the the lower trigger limit, we substitute V out as VCC plus, and then just do the math. It's trivial because we already have it as our trigger limit voltage is a function of the reference voltage and the output voltage, which are known quantities. So this is all the analysis we really need to do for the inverting Schmitt trigger. We recognize that these two voltages change position, which means they change position in our equation, and we're done. All right. So I'll literally write VCC minus for UTL, VCC plus for LT. And that's how we get our upper trigger and lower trigger limits. So let's see. In this case, R1 is 1 and R2 is 5. So for our example here, since Vreference is still 0, that's going to get thrown away. So we're going to have 1/6 times -10 volts, -10 over 6. Yeah, -10/6. I'm just going to write it as that. So that's when our output exceeds that, or excuse me, when our input gets there. We have our upper trigger limit. For our lower trigger limit, it's going to be 1/6 times +10 is +10 over 6. So let's change this real quick and just observe that it's working how we expect it to. So all I got to do, delete, move this dumb thing out of the way. Vn. No, that's not what I wanted to happen. Vn versus V out. And it's a bit harder to see that this isn't occurring at exactly 2. It's occurring slightly before 2 and then slightly before -2, which 10 over 6 is 1 2/3. So +1.67 and -1.67 If we plot it with the input voltage, it might be easier to see. And it is, if I can get rid of this thing. So we still have our hysteresis as we had before, but we can see that our trigger limits are positive 10/6 and negative 10/6. So easy peasy. All right. The last thing that I want to talk about today, I'm not sure if this will take the full half hour, but it'll be okay if it doesn't, is the Stable Multivibrator circuit. Right. And specifically, it's the op-amp variant of this. So a stable multivibrator or oscillator op-amp circuit. Okay. And that circuit looks like this. Now, I want to be clear. What I have just drawn is a negative feedback loop because it's from the output terminal to the inverting input terminal. But there's also a feedback resistor on the positive feedback side as well. This guy is R1. In addition to this, we have a resistor here, which we're going to call R2. And we also have a capacitor here, C, and this point, this corner, is our ground, okay? This is the completed circuit. Do you notice anything odd about it? Got a capacitor in it. All right, that is something odd. Probably not the most odd thing. What's another odd thing? There's no input voltage source anywhere, okay? So this is an astable circuit. Does anybody know what astable means? There is no point of stability in this circuit, okay? So that means it oscillates back and forth between, because it's a positive feedback circuit, it's going to oscillate back and forth between VCC plus and VCC minus. It's never going to settle to a specific value. There is no input voltage, meaning if you wire this guy up to a practical op-amp circuit and you wait, it will start ringing between VCC plus and VCC minus, and we'll see that exact same thing when we simulate it in a minute. Let's talk about what the heck is going on here, okay? So let's start. I know this is going to sound weird, but let's start by assuming that the output voltage is positive, okay? So if we assume that the output voltage is starting out as positive, that means that the voltage present at the non-inverting terminal right here, which is effectively our reference voltage. So let me write that down. Vref. This voltage will simply be V out multiplied by R2 over R1 plus R2 because it's a simple voltage divider circuit, right? We can see that. So our reference voltage has some positive value based on the ratio of these resistors and the output voltage being positive. This also, if V out is positive, means that current can flow through this resistor and start charging this capacitor up, okay? So what we should see, if we plot what's happening here, one, two, three, four. So here's where all my voltages as a function of time are going to go, and here is time. So our output voltage, which I'm going to draw in, I guess, red, it's starting as positive, okay? As long as the output voltage remains positive, our reference voltage will also be positive. And our capacitor voltage, which I will do in orange, I guess, is charging. As soon as the capacitor voltage hits the reference voltage, this thing switches, the output switches polarities, okay? So as soon as VC So let me draw a little legend here, I guess, since it'll make things easier. The red curve is V out, the blue curve is V ref, and the gold curve is VC. So as soon as the output, excuse me, as soon as the capacitor voltage hits V ref, the system switches stability points, okay? So the capacitor is going to see a negative voltage, which means it's going to start discharging. It takes time for it to discharge. So we have something like that. This guy, that's the wrong color. And the output also goes slow. So this is VCC plus, here's VCC minus. This is VREF plus and VREF minus, because the reference voltage is constantly going to be switching polarities as well. And this system just oscillates between these two states over and over and over, like so. Where this time distance, so for one full cycle of this guy, is the period of this function. And I'm choosing not to start at where we have t is equal to 0 because the capacitor didn't go through a full cycle there. This period, t, is equal to twice RC times the natural log of 1 plus beta divided by 1 minus beta, where beta is the resistor ratio R1 plus R2 which sets our reference voltage. So we now have a tunable resonator circuit. We choose the amplitude of the output by selecting our power supply voltages, and we can change the frequency by either putting a potentiometer R in the negative feedback position or putting a potentiometer within the positive feedback portion as well. So we can tune the frequency of this guy. So this is something I was literally asked about yesterday. One of the senior design groups is making a tremolo circuit. They're making their senior design project is making a couple of different effects pedals for guitars. And so they were trying to figure out a frequency tunable circuit that would cause an LED to blink at different frequencies. If you put an LED on the output here, and you chose VCC minus as ground, effectively what this circuit acts like is an on-off switch for this LED. So at one particular frequency, it'll blink. And then if you use the potentiometer to change the frequency, it would blink at that new frequency. Again, they're using that because they're using this to drive the LED, and then they're using a photo detector to drive the tremolo circuit to effectively measure the frequency that's oscillating at, and then use that to change the guitar signal. So anyway, it's a useful little thing. There's another group that's using the BJT version, where with the BJT version, you wind up with a sinusoid instead of a square wave. But anyway, this will show up a lot in tunable resonator circuits. So as you progress in your degree, this is a very, very useful thing. All right, so let's simulate this guy because I want to show you something potentially wonky about LT Spice. Potentially wonky and also incredibly useful. So I want to close this and just create an entirely new one. Do I want to save changes? No. Don't want to open anything. All right, so let's start with our good old universal op amp. Slap that bad boy in the middle. I type in UNI for the universal op amp. That's it. Yeah. If I go to this thing that looks like a digital or for whatever reason says component, I click on that. There is, let me back out to the beginning thing. So in addition to basic circuit components, not even entirely sure what some of these are, to be honest. So I know like NPN, NPN2, NPN3, and NPN4 are different numbers of terminals for BJTs. NMOS is a 3-terminal, NMOS4 is a 4-terminal, meaning you have body effects. This is a N-type JFET, blah, blah, blah. Anyway, over here, there's a full menu of op amps created by Analog Designs, Linear Technologies, and I think one other company. At the very, very end of that is a universal op amp model, which has all editable parameters. So we can change that. It's a generic op amp effectively that we can change stuff on. So that's the one that I like to use. Okay. So first thing I'll do is get those power supply voltages out of the way. And just for the sake of argument, let's do 5 and -5. All right, so my negative feedback path. Positive feedback path. Here's resistor R1. Over here will be resistor R2. And up here will be that resistor that I just have labeled R. Oh, I'm sorry, you're correct. That should not have happened that way. Yeah, thank you for noticing that, or I would have been very stumped as to why this wasn't working right. Get this stupid zoom thing. I guess I'll put it down here for now. For my capacitor. There. All right. Be lazy. 1 millifarad. 1 kilohertz. Or excuse me, 1 kilo ohm. And then 1K. And 1K. And I do need to specify that this is ground or it won't work right. But I'm about to do something and it's going to look like it's not working right anyway. So simulate. Let's do it for 10 seconds. And run. Soon to fit. All right. So if I look at my output node, I get an output of 0 volts. Okay. Why this is happening is because I haven't forced an initial condition on this circuit to kind of kick it off. Because this is an idealized op amp. It requires that. So just to show you exactly what I mean by that, I'm going to cut that guy off for a second and replace it with a LT1001. So this is a Linear Technologies model op amp with its own defined parameters and all that kind of jazz. And I run, and it's not doing remotely what I thought it would be doing. The voltage changes, but it's taking more time. Let me, let's look at it over 100 seconds and see what happens. All right, yeah, so after about 38 seconds or so, the capacitor finally has enough energy to actually kick on, and then it starts swinging between 4 volts and -4 volts. So the reason why it's not hitting VCC plus and VCC minus, this particular op amp isn't a rail-to-rail op amp. So to make this work with our universal op amp, UNI. So to make sure I'm not pulling your leg, we'll run this exact same simulation over the 100 seconds. It still shows up as exactly 0. What I'm going to do is I'm going to put in a SPICE command. .IC. Actually, I need to do something real quick here. So this node is node 1. Okay. So .IC V, so voltage at N001. I'm saying the voltage that is at that particular node is equal to 1 volt. I am putting some initial energy into the system. In LT SPICE, we can only set initial conditions on capacitor voltages and inductor currents. So there's no way for me to declare that the output voltage here is 10 volts. So I'm just saying, well, the capacitor has some voltage across it. Let's see how that affects the system. So if I do that one little thing and then rerun, boom, I get my +5 volt the negative 5 volt oscillation.
So 1 volt is just a start.
Yeah, exactly right. So let me see something. I didn't test this, but so let's say that I have a millivolt on that capacitor. Now it takes a little bit of time to swing up, right? So I'm just kick-starting the energy is all that's happening there. And the smaller the voltage I apply across the capacitor, the longer it's going to take for the feedback to ramp up and make it swing. That's all that's happening. Is when we start with a low amount of energy stored in the capacitor, it takes time for it to cycle back and forth until we get that cascading positive feedback that causes it to go rail to rail. All right, so sure. So 2 ways we can do it. One, when I put my voltage probe over it, it says VN001. So that's one way. Or I can put a marker on here. So I could call this VC. And then I can edit this to be the voltage at the node I've labeled as VC. And it does the exact same thing. So this putting initial conditions on things, this is going to, excuse me, when you're doing homework regarding transient analysis, this is exactly how you can do it. You can draw the circuit for t is equal to 0 plus and beyond, and put the initial condition on your capacitor voltage and or inductor current, and it will plot the transient analysis, and you can literally type out the mathematical function and make sure that they overlap each other to check your work. Which after we finish op amps and let's say we have negative feedback on Friday, cascaded on Monday. So we should be getting into transient analysis at the middle to end of next week. This will save you tons and tons of headaches because you can literally see, did I do my homework right or not, without having to go through the steps, because the math isn't particularly hard, but until you get used to it, it's going to look real wonky because we're going to be solving second order differential equations for various different systems, which some of you may not have had math 245 yet. So that's going to be like, what the hell are we doing? So this will help the, oh God, what's happening of your class for a little bit. All right, it's 12:10, so we're getting out 5 minutes early. That's good enough for me. So I'll see you guys on Friday. We'll talk about more of it. Yes, sir. Sure. And that's the wrong thing. That's the right thing. I need to do a, excuse me, a roll sheet real quick because I forgot about it. So let me send that to you.